Okay, we're going to work with example 2, and this is coming from the 3.7 optimization. And on this one, we have a river. Read the problem. We've got this river that flows through some farmland, and they want to pasture off a rectangular pasture. So, I know on my picture it doesn't quite look like rectangular, but we're going to have this side bordered by the river. I'm going to call one of these dimensions x, and the other one, let's grab a pen here, this will be x and this will be y. Now, a farmer plans to fence a rectangular pasture adjacent to the river. The pasture must contain 151,250 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? So really all we have to do is fence along 3 sides of this. So I know that my fencing, I'm going to call it F, is equal to x plus y plus x, so 2x's plus a y. And then the other thing that we were given was that we had to have 151,250 square meters. So that would be the area of this 151,250 is equal to the area of our pasture, which would be x times y. Now, which is the helper equation, which is the primary equation? Because this is what I want to have the least of. I want the least fencing. That means I'm going to minimize this particular equation. So this is what I'm going to refer to as this is the primary equation. It's what I'm going to take the derivative of. This other equation is really going to act as our helper or our constraint equation. Now, so what I want to take the derivative of is f equals 2x plus y. But that has 2 variables. So let's use our helper equation off to the side here and just quickly calculate out, solve for one of the variables. So if I divided by x, that would give me the y value, right? So if I just come in and divide by x, I'm going to have my y. So now let's substitute over here for y. So that's going to give me f equals 2x plus 151,250 over x. And now what we want to do is take the derivative of that. So f prime, everything's in terms of x, f prime of x is equal to 2 minus, and remember we could think of this as x to the negative 1, so I'd have minus 1 coming down, multiplied by this coefficient, and that's going to drive this to an x to the negative 2, so I'll have x squared underneath. Now let's minimize by setting this equal to 0. So 0 is equal to 2 minus 151,250 divided by x squared, and solve. So since this is negative, let's think about adding that to our other side, and that's going to give me the 151,250 over x squared equals 2. Multiply up by that x squared, 151,250 equals 2, x squared, divide by 2, and we will come up with x squared equals half of that. So calculate. Okay, so that was equal to 75,625. Now let's take the square root of both sides, and we could have plus or minus, but because we are working with fencing, it would make sense that we'd only have a positive square root. So 75,625. The square root of that actually is a very nice number, 275. So we just figured out one of our critical points here, right? Because we set it equal to 0. This is, at this stage, we were going after critical points, just like we worked with in max and min problems. And that suggests that the x value is 275. If you did a quick sign chart on that, 275 is our x value, f prime, and we put something in under that. Maybe coming back into here, I believe you'd find that was negative and this was positive, so it's a decreasing, increasing scenario, and that gives us the minimum amount of fencing. If we go back up, then I know that x is equal to 275, and we can find y value by plugging it in. And at this stage here, we knew that 151, 250 divided by your 275 will find y for us, and y will come in at 550. I was using this formula, plugging in my 275. Very good. On to the next problem. The open box. An open box is being constructed from a piece of sheet metal 18 inches by 30 inches and cutting squares out of the corner. So we're going to have an open top box, basically. We want to maximize the volume, and then what would the volume be? Okay, so I just drew in some dimensions. We have 30 inches on one side by 18 on another. We're going to be cutting out these corners, so this portion's gone and this portion will be gone. These are the square corners we're going to cut out so that we can lift the tabs and form this into a box. Now, what I'm going to cut is a depth of x and then a depth from the side inward of x. And we would do that all the way around this box, the dimensions of these squares being cut out from the corner tabs. What it leaves us is the interior of this box, and let's just go put this crayon on here, so that the base of our box is really going to show up right in here. And what I need to know then is what is the dimension, or the dimensions of that. So how long will that be? Well, that's going to be then 30 minus the x from each side, so 30 minus 2x is my cut there, and the width is going to be 18 minus 2x, and that will give us that interior base dimension. So an open box is being constructed, and we want to make sure we have maximum volume. Well, just think about volume for a second of a rectangular prism, length times width times height. In terms of our box, what we're looking at here is volume is equal to 30 minus 2x, 18 minus 2x, and a height, when those flaps get lifted up, you would have a depth then of x. So that'll be the height of our box. This is the equation we are going to want to maximize, right? This entire equation. We could use a product rule. It would take a few steps because we've got three terms being multiplied. I think easier would probably be to FOIL this and then take the derivative once we get it in a polynomial style. So let's just quickly FOIL this out. 30 times 18 gives you, well, 3 times 18 will be a 4, so 540, and a minus 60x, a minus 36x, and a plus 4x squared, all multiplied by x at the end. So go ahead and FOIL this out, come back, maybe pause for a moment. Okay, I got mine down to the polynomial. Now let's go in and do our derivative. So v prime is equal to 540, double the 96, that becomes 192x plus 12x squared. And I want to set it equal to 0 so that I can find my critical points. Let's go ahead and factor a 12 out. 12 will go into each of those terms up there. So it gives me 45 minus 16x plus the x squared. This is factorable, so let's factor that. X times x, and then that's going to give me, maybe it isn't factorable, 9, 5. Not so much, is it? So A little bit of work here to do. Let me erase this. Let's go back since that's not so factorable. And what could we do? We could use the quadratic formula. That would be one option. We could also work on completing the square. So perhaps that's what I will do. Let's divide by 12 and get rid of the 12 on each side and just get this down a little bit easier. So 0 is equal to x squared minus 16x plus something plus the 45 minus whatever I'm bringing in. What I'm doing is setting up to do the complete the square. So take the middle term, divide it by 2, and square it. So we get 8. 8 squared is 64. 64 is our magic number to bring in for completing the square. Now that makes this factorable into an x minus 8 quantity squared minus 19, where this is coming together to make that negative 19. Bring the 19 over, I have 19 is equal to x minus 8 quantity squared, square root, and we're x minus 8. That leads me to say that x is equal to, add 8 to that, and we're at 8 plus the square root of 19. Now, when I square root it, I should have a plus and minus going on here. So plus or minus the square root of 19. Only one of these is in the domain. 8 minus the square root of 19 is approximately 3.6, which will work because it will not extend beyond the halfway point. What I'm looking for, this is my least side. So when I take 18 and subtract 2 times that value, which was about 3.6, or 7.2, halfway point on this box would be at 9 inches. So I can't make a cut deeper than 9 inches in, or we will be going beyond halfway and no box will be remaining. You cannot cut tabs that big. So I think this is the only one that'll work. The 8 plus square root of 19 will be obviously too big and won't work. So, and then from there we can plug this value in.